All right, for those of you that are in Zoom, please type something into the chat to let me know that you are present. I did unmute myself. All right, so today we are going to talk about the transient analysis of series RLC circuits. And let's not do it all in red. All right, so let me draw a quick picture of a series RLC circuit. So we have some basis with which to talk about. So I'm going to call this voltage V naught. It is going to be connected to this guy where we have some resistor R connected to some inductor L, connected to some capacitor C. Like so, and this switch is opening at T is equal to 0. So we have a very similar case as to what we observed last Friday. For this circuit, because at T less than 0, the inductor looks like an open circuit, or excuse me, a short circuit, and the capacitor looks like an open circuit, we'll see that our capacitor has some stored energy. And when the switch opens, the capacitor will transfer that energy to the inductor and to the resistor, kind of passing it back and forth until the resistor converts all of the stored energy into heat. So during the transient condition, we can write another, let's see, in this case, it would be a Kirchhoff's voltage law relationship. So let me identify a couple of things. I'm going to say that this is my common current I of T. Let me see what Miss Bailey is saying. Oh, let's see. Bailey, you said here and then you raised your hand. What is what's going on? Or is that just you letting me know that you're here? Okay, not a problem. All right, so I'm going to define my current I of T, which will be common to my series RLC circuit. And I'm defining it in a specific location so that you will, generally speaking, associate it with the inductor current because it is representative of the inductor current, which we know cannot change abruptly and all that kind of good stuff. So based on the direction of this current, I'm going to have some voltage VL of T like so, some voltage VC of T like so, and some voltage VR of T like so. The reason why I've chosen the positive polarity on bottom for the resistor is so that the current is entering the positive polarity, so that all three of these elements are depicted as absorbing power, just a convention that I prefer to use. So I can now write my Kirchhoff's voltage law relationship where I would have VR of T plus VL of T plus VC of T is equal to 0. And all three of these voltages can be related back to our common current I of T. So using Ohm's law, we would have R times I of T plus let's see, current voltage. Okay, sorry, had a brain fart there. L di by dt plus 1 over c, the integral from t naught to t of I of, let's do x, dx plus some initial condition on my capacitor voltage. Set that all equal to 0. And again, we have a integral differential equation, which we can get rid of the integral part by taking the derivative of both sides. So rearranging, we are going to have L times the second derivative of our current plus R times the first derivative of our current plus 1 over C times our current is equal to 0. And I'm going to divide through by a factor of L, which leaves me with second derivative of the current plus R over L times the first derivative of the current plus 1 over LC is equal to 0. I'm going to make a guess as to the shape of my current, and I'm going to guess that it's going to be of the form AE to the ST, which is the exact same guess we made in our last class period with regards to the capacitor voltage in our parallel RLC circuit. And in doing so, I get S squared AE to the ST plus R over L S AE to the ST plus 1 over LC AE to the ST is equal to 0, which I can rewrite as A times S squared plus R over LS plus 1 over LC times E to the ST is equal to 0. And I now have my characteristic equation. So from my characteristic equation, I can determine my eigenvalues of my system. Since it's a quadratic equation, I will have S1 is equal to negative B, so that is negative R over L plus the square root of R over L quantity squared plus 4 times 1 over LC, so 4 over LC, all divided by 2, which simplifies to negative R over twice L plus the square root of R over 2L quantity squared plus 1 over root LC quantity squared. And similarly, S2 will be negative R over 2L minus square root of R over 2L squared plus square root of 1 over LC squared, like so. And this leads me to the exact same point that we were with our parallel RLC circuit, where I'm going to define now alpha and omega naught for a series RLC circuit. So alpha, which is still our Neper frequency representing the attenuation of the signal, is R over 2L. Omega naught, the resonant frequency, is the square root of 1 over LC. And we can use these guys to find that S1 is negative alpha plus the square root of alpha squared. Sorry, those guys should be minuses because it's minus 4AC minus omega naught squared. And S2 is equal to negative alpha minus square root of alpha squared minus omega naught squared. Pardon? How did I get the 4 or how did I get rid of the 4? So speaking specifically about this guy, right? So the quadratic equation is negative b plus or minus the square root of b squared minus 4ac, right? So that's where the 4 came from. It's cool. It's been a long time since 8th grade, man. Not a problem. And then when I move that factor of 2, that's why the 4 goes away. Yeah, not a problem at all. All right, so we have eigenvalues. They have the exact same relationships that we saw with a parallel RLC circuit, meaning if alpha is greater than omega naught, we have an overdamped system. If alpha is equal to omega naught, we have a critically damped system. And if alpha is less than omega naught, we have an underdamped system. The only difference between a series RLC circuit and a parallel RLC circuit is that alpha has a different value, right? So alpha has gone from being 1 over 2RC to R over 2L. That's it. That's the only difference whatsoever. So from here on, our approach to analyzing any series RLC circuit will be literally the exact same thing that we did. So wrapped up in 15 minutes. No, I'm kidding. Let's work an example problem or 2 just to kind of solidify things, and then we may actually wind up getting out of here. So the last problem that we worked was a underdamped system. So I'm going to try to make the math work here to give me an overdamped system, and we'll see what's what. So let's say that we have the following circuit. $10 volts, 10 ohms, 2 henries, oops, need to put my switch in there, and give me just a minute to calculate a value of C that will force this thing to behave the way I want it to. Let's see. Okay, that'll work. 1/2 of here. So I believe I'm using the exact same component values as we had before, but because we have a series RLC circuit, having a large resistor makes it be overdamped, whereas in a parallel RLC circuit, having a large resistor makes it be underdamped. All right, so our steps are going to be literally identical. So the first thing we're going to want to do is calculate alpha and omega naught, and then determine whether the circuit is critically damped, overdamped, or underdamped. So alpha is R over 2L, which is going to be 10 ohms over 4 henries, is 2.5 nepers per second. Omega naught is 1 over root LC, which is 1 over the square root of 1, which is 1 radian per second. So obviously, alpha is greater than omega naught, meaning that we have an overdamped system. So while we're at it, let's calculate S1 and S2. where, just to be clear here, S1 is negative alpha, so that's negative 2.5 plus the square root of alpha squared, so 2.5 squared, minus 1, negative 0.2087, and then S2 becomes negative 4.7912. And the units on both of these are per second or hertz. And I'm going to store these in my calculator to save me a headache later. A and B, just reminding myself of what I have them stored. All right, so that's step one taken care of. We know all the information about the system so that we can characterize its response. Now we need to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our circuit looks like this. Here is our common current, I at 0 minus. Here is our inductor voltage, VL at 0 minus. Here is our capacitor voltage, VC at 0 minus. And again, the resistor doesn't play a part. But let's cycle back up to our beginning schematic here and identify a quantity of interest that we actually want to solve for so that we have arguably some amount of direction, right? So you guys pick two quantities that you want me to solve for. Voltage drop over capacitor or inductor or resistor, current through capacitor, inductor, or resistor. Just make sure both of them aren't resistor quantities and we'll be good to go. Tell me something. All right, so the voltage drop over the capacitor. And to be specific, what direction? I'm going to assume positive polarity up there. Which I guess I should have assumed I of t to be in this direction based on that. What direction do you want for the resistor current? Flowing down through the 10 ohm resistor or up through the 10 ohm resistor? Flowing down. All right. So let's call this guy right here IR of t. Okay. Okay. So now circling back around to the problem at hand, we're analyzing this guy at t is equal to 0 minus. So we need to get numerical values for I at 0 minus, VL at 0 minus, and VC at 0 minus. So who can tell me what any of these quantities are? Let's start with the easy ones. They're actually done in the order from easiest to hardest. I is 0, right? It's a current flowing through an open circuit. So by definition, it must be 0 amps. What's the voltage drop over my inductor? 0, because it's a voltage drop over a short circuit. So from that, what is the voltage drop over our capacitor C? Pardon? Same as the voltage drop over the resistor, which is exactly 10 volts. All right. So our analysis, pretty dang easy, right? Let's move along to analyzing the circuit at t is equal to 0 plus. At t is equal to 0 plus, our voltage source has been disconnected, so I'm no longer going to bother drawing it. So we have our 10 ohm resistor. We have our capacitor is going to be replaced with a voltage source having the same polarity as VC and the same magnitude. And what am I going to do with my inductor here? I know that my inductor current can't change, so if it was 0 amps, it needs to continue being 0 amps. So how am I going to represent that? Open circuit. All right, so VL 0 plus goes there. Our analysis should be fairly straightforward. I at 0 plus has to stay at 0 amps because that's what it was. The L at 0 plus will be something new potentially. The C at 0 plus has to stay at what it was, so it's 10 volts. So who can tell me what VL at 0 plus is going to be? Negative 10 volts, right? Because when we do Kirchhoff's voltage law around that loop, the answer has to come out to 0. We know that no current is flowing through that resistor, so we have VL plus 10 volts is equal to 0, so VL has to be negative 10 volts. All right, so there's our analysis at t is equal to 0 plus. Again, just a stunning amount of circuits knowledge being applied, right? So now we're ready for step 4, which is to apply our response equations. So we're looking for the capacitor voltage and the resistor current. I believe that we can get both of those quantities by using our capacitor response equations, okay? So let me explain what I mean by that. So we're going to be focusing our analysis, our response analysis on the capacitor because we can get the voltage drop over the capacitor fairly easily. And the current flowing through the capacitor is the exact same thing as the negative of the current flowing through the resistor, right? So if I can calculate VC and IC, I can get all the information that I actually want. So that's why I'm focusing on my capacitor relationships. So because we have an overdamped system, VC of t will be of the form A1e to the S1t plus A2e to the S2t, right? Right off of your spreadsheet or table or whatever the hell I've been calling it that I gave you guys. And from this, VC at 0 simplifies to what? What happens to my exponential functions? At t is equal to 0. They both go to 1. So I just have VC is equal to A1 plus A2, which gives me an equation. A1 plus A2 is equal to 10 volts, right? So whenever I had the underdamped system, it was, I guess, arguably more complex because I had that omega D I needed to care about, and it was, you know, the sinusoids and all that jazz. But I knew the exact value of one of my coefficients right off the bat. In an underdamped system, unfortunately, we do not. We're going to wind up having a system of equations that we have to solve. But it's just going to be 2 equations, 2 unknowns, so it's not going to be that particularly difficult. All right, so our current IC of t is C dV by dt, which is going to be C times S1 A1 e to the S1t plus S2 A2 e to the S2t. At t is equal to 0 plus, this is going to reduce to what? And all of that multiplied by c. You can't forget c, right? Yeah, so our exponential functions both go to 1. So we're left with c s1 a1 plus s2 a2. And so this gives us c s1 a1 plus c s2 a2 is equal to our current, which was 0. Crap. So this is equation 1. This is equation 2. So we now have enough information to solve in our system because we know what the value of C is, and we know what the value of S1 and S2 are. And in this case, because we're setting this equal to 0, because our current had a value of 0, the C doesn't particularly matter. We can divide through by both sides by C and be okay. So I'm going to set up this simple 2x2 system in my calculator real quick. So let's see, I'm going to have 1 and 1 is equal to 10. And then here I'm going to have S1, which I have stored as variable A. S2 I have stored as variable B. So they're equal to 0, solve. And I get A1 is equal to 10.455 volts, and A2 is equal to 0.455 volts. Yeah, sorry, you're absolutely right, negative. Thank you. So from this, VC of t is 10.455 e to the negative 0.2087 t minus 0.455 e to the minus 4.7913 t volts. IC of t, so I'm going to have that same e to the minus 0.2087 t here, and I'm going to have that same e to the minus 4.7913 t here. My answer is going to be in amps. My first coefficient is just going to be C times S1 times A1, right? So that's 1/2 times S1 times A1. I get negative 1.0910. And for coefficient 2, I have C times S2 times A2. Which is positive 1.0910. And that makes sense because I know that at t is equal to 0, my total current should be equal to 0 as well. So those coefficients have to exactly match each other. Oh, from this, IR of t is negative IC of t. And so that would be 1.0910 e to the minus 0.2087 minus 1.0910 e to the minus 4.7913. We have determined both of the quantities that we were in. So that was a series RLC circuit having a different response than one that we have seen before. Knocked it out. Pretty easy. So what do you guys want to do now? What's up? So S1, S2 were from these guys right here. Yep, nope, no problem. Yes, the sheet is on Moodle. If you go to, let's kill some time and find it real quick because I really don't have anything much else to talk about unless you guys want me to talk about other things. ELEN 223. All right. So if we go to class meeting number 8, which was last Friday's lecture, the sheet is right here where it says table of parallel and series RLC responses. Okay. All right. So we technically still have 40 minutes left of this class. So let me posit something to you guys. Our next topic to be discussed, according to the syllabus, is the total response of series and parallel RLC circuits. Legitimately, we can cover that topic in roughly about the same amount of time that we covered this one. So what would you guys say to taking care of that today and then not having class on Wednesday at all so that I can get out for an earlier Easter break? Sound groovy? Actually, I can't because I have a lab that afternoon, but still, we'll do it anyway. All right, so everybody okay with doing that and just not having class on Wednesday? All right. So let's think about, let's scroll back up here to the top and think about what would happen if that switch flipped in the other direction. So instead of opening at t is equal to 0, it closed at t is equal to 0. All right. We would start with a system that has no stored energy whatsoever, and a very long time after the switch closes, we would have a system that does have some stored energy. In this case, because of the way that the system is set up, at t is equal to infinity, we would see that the inductor is a short circuit, the capacitor is an open circuit, and therefore the capacitor would be the one with stored energy, and then the inductor would have no stored energy. So we would see that the capacitor would have a total response look to it, while the inductor would have a natural response look because it's decaying to some value where it has 0 current at the end, but the capacitor voltage has some value that's non-zero. The only change that we need to make to our circuit analysis or to our process is twofold. Our response equations for y of t have to now include a plus y at infinity term to accommodate the fact that our signals can settle to some non-zero value. And we just have to analyze the circuit at t is equal to infinity as well. Those are the only changes that we have to make, okay? So let's come up with an entirely new problem here. You guys care if it's series or parallel? Anybody care? Series or parallel? All right. Let's do a series because that's what today is about. Let's try to do something slightly less boring. Let me think about this real quick. Change the direction of this guy. So this one's going to be closing. This one's going to be opening. And this will be a 2 amp current source in parallel with a 5 ohm resistor. All right. And because we haven't worked one yet, we're going to come up with some component values that are going to force this guy to be critically damped. Okay? So let's look at those relationships real quick. For critical damping, we require that alpha and omega naught be equal, right? So I guess the first thing that I want to ask here is, does everybody understand why this is going to look like a series RLC circuit after sorry, let me make one small extra change here. All right. So I needed to do that because it was going to look like an LC circuit, according to the transient analysis, which would be okay, but that just means it's going to oscillate forever, which is not really what we're looking for. So when we're looking at this guy during the transient condition, that means that this guy over here has been completely disconnected. And so we just have this voltage source that is connected to our resistance network in series with an inductor, in series with a capacitor. If I'm looking at the Thevenin equivalent resistance, which is how I would look at this thing from a natural response perspective, and that's important because our total response is just our natural response plus our forced response added together, I would turn this voltage source off, which will just put these two resistors in parallel with each other. So I would have a single resistance in series with this inductor, in series with this capacitor, which looks like a series RLC circuit. All right. So then this begs the question of how am I going to get some values? All right. So we know that alpha is equal to R, which in this case is going to be R1 in parallel with R2 divided by twice L. Actually, let me just put that as REQ, where I'm going to wind up confusing myself. Over 2L, and omega naught is equal to the square root of 1 over LC. If these guys are equal, then that gives me REQ over twice L is equal to 1 over the square root of LC, or my equivalent resistance is equal to 2 times the square root of L over C. Right? So if I have L divided by the square root of L gives me a square root of L in the numerator. And then square root of C is still in my denominator. And I have a factor of 2 that's going to be outside. All right, so let's choose some values to make some things work here. All right. Let's say that I want L over C to be 25 because I can take the square root of that pretty easily, right? So L needs to be 25 times larger. So let's make this 25 millihenries and 1 millifarad, and that part works out. And REQ just needs to be 10 now in order for this guy to be critically damped, right? So I'm going to do a 20 ohm in parallel with a 20 ohm, and we're good to go. All right, so we should see that we have a critically damped system. So alpha is going to be 10 ohms over 50 millihenry. Is 200 amperes per second. Omega naught is going to be 1 over root LC. Let's see, L is 25 times 10 to the minus 3. C is 1 times 10 to the minus 3. 200 radians per second. Alpha is equal to omega naught, means that we have a critically damped system. Okay, so shows my numbers correctly. Force this to happen. All right, so step 1 is taken care of. Step 2, analyze the circuit at t is equal to 0 minus. This one's going to be a little bit more difficult, just based on the increased level of complexity, but it shouldn't be too difficult, right? So at t is equal to 0 minus, our leftmost switch is still open and our rightmost switch is still closed. So if our leftmost switch is open, we're going to have something that looks like this. Our inductor is going to be a short circuit. Our capacitor is going to be an open circuit. Our right switch is closed. So here we have our current source, which I believe I said was 2 amps. And then we have our 5 ohm resistor way out over here. So let's define some quantities here. This is going to be VC at 0 minus. This will be VL at 0 minus. This is I at 0 minus. And we're only going to worry about our last step or whatever is going to be just finding the inductor current for this guy, just because it's reasonable. Let's see, what was the value of that voltage source? Doesn't matter because it's not connected, but still useful to draw. 5 volts. Okay, so we have our 3 quantities that we need to be keeping track of. I at 0 minus, the L at 0 minus, and the C at 0 minus. You can tell me what any of those 3 quantities are going to do. How did you get that? Let's start there. Yeah, so you're saying you did a source transformation here, so you had 10 volts in series with 5, in series with 20. So that's valid, but you didn't do the voltage division necessary to give you the correct answer. So based on that style of assessment, I would say that it should be 8 volts. Another way that we could do this is 2 times 5 in parallel with 20, right? So that's 2 times 5 times 20, so 2 times 100 over 25, 2 times 4 is 8 volts. You get the same result either way. So VC at 0 minus should be 8 volts no matter how you choose to approach that, right? The using a source transformation is actually a pretty smart way to go through there and do it pretty quick. All right. What is our, what's another quantity? VL is 0 because it has to be, right? It's a voltage drop over a short circuit. So we're left with I at 0 minus. Multiple ways that we could approach this. Knowing what the capacitor voltage is, in my opinion, makes this significantly more easy, right? What I mean by that is we know that no current is going to flow through this guy. So all of this current I at 0 minus is flowing through this 20 ohm resistor. The voltage drop over that 20 ohm resistor is VC because they're in parallel, right? So we have 8 volts divided by 20 ohms. So that is 4 over 10, so 0.4, and the current is flowing into the negative polarity terminal of the resistor. So we should have negative 0.4 amps, I believe. Yeah, and that negative sign also makes sense from a current division perspective, right? So based on current division, we know that this 2 amps is going to split between the 5 and the 20, and we should expect to see that, let's see, 80% of it flows through the 5 ohm resistor, 20% of it flows through the 20 ohm resistor based on those ratio of those resistances. So 2 times 0.2 is 0.4, but the current is flowing in the opposite direction that we would expect, so that's where the negative sign comes from. So again, whatever way you choose to analyze it is perfectly okay. You will, if you do things correctly, get to a result that I is negative 0.4 amperes. So our circuit has been successfully analyzed at T is equal to 0 minus. We good with that sentiment? Anybody got any questions, comments, concerns about any of the analysis that we did? All right, nobody's saying much anything. So now we analyze a circuit at T is equal to 0 plus. So at T is equal to 0 plus, our leftmost switch is closed and our rightmost switch is open. So this 2 amp source and this 5 ohm resistor are completely thrown out. We don't have to deal with them anymore. So, oops, not what I wanted. This 20 ohm resistor is still a 20 ohm resistor. This 20 ohm resistor is still a 20 ohm resistor. So my inductor is going to look like a current source with a direction the same as I and a magnitude the same as I. So this is going to be a negative 0.4 amp current source. Our capacitor is going to be a voltage source, same polarity as VC, same magnitude. So we have an 8 volt source there. So this is our new circuit. And this is VL at 0 plus. So if that's the polarity we had at 0 minus, that's the same polarity we have to keep at 0 plus. We know that I at 0 plus has to continue being negative 0.4 amps because it is the inductor current, so it cannot change abruptly. We know that VC at 0 plus has to continue being 8 volts because it's the capacitor voltage and it cannot change abruptly. The only thing that we don't know is VL at 0 plus. So how might we go about determining that quantity? Pardon? Nodal analysis. Okay, that seems reasonable enough. So what do you want to choose as our reference node? The bottom. All right. So here is our reference. Here is the only node, I'm just going to call it Vx, that we don't know the voltage of. So if we do Kirchhoff's current law at node X, we have Vx minus 5 volts over 20 ohms plus Vx over 20 ohms is equal to, those are the currents leaving, oh, actually, no, that's not, all of the currents are leaving node X, minus 0.4 amps is equal to 0. Solve for Vx, right? So that's the current directed to the left, plus the current directed down, plus the current directed to the right is 0. So we successfully applied KCL at node X. So I'll stop talking and do the math and figure out what Vx is, unless you got a number for me. 6.5? Nothing, just straight up 6.5. All right, Vx, 6.5 volts. Anybody else get that? Or are we willing to trust this gentleman's ability to use his calculator? You got it too? All right, so 2 of us got it. Good enough for me. What is VL? Now that we know Vx. Right, so it'll be Vx minus 8 volts is negative 1.5 volts. All right, seems groovy to me. So this is one of those places where we have to add an additional step, right? Because we have a source still in our system. During the transient condition, we have to analyze our circuit now at t is equal to infinity. So at t is equal to infinity, our switch on the left-hand side remains closed. Our switch on the right-hand side remains open. The only change that we're going to see is that our inductor now looks like a short circuit and our capacitor now looks like an open circuit. So at t is equal to infinity, we have this guy. $20 ohms. 20 ohms. Here is I at infinity. Here is VC at infinity. Here is VL at infinity. So let's write these down. I at infinity is going to be something. VL at infinity will be something. VC at infinity will be something. Who can tell me what the value of any of these quantities are going to be? Current's going to be 0. Okay, I agree with that wholeheartedly. Current flowing through an open circuit has to be 0. VL is going to be 0 because the voltage drop over a short circuit has to be 0. Okay, we got 2 out of 3 taken care of. What about VC? The voltage drop across the 20 ohm resistor. Okay, let's see what chat says. VC is 2.5 volts. Absolutely right. Because we know that the voltage drop is going to distribute itself evenly over those 2 identical 20 ohm resistors. So that's absolutely perfect. Thank you for the Zoom coming in and letting me know that you're paying attention. All right. So that is all of our circuit analysis at t is equal to infinity. Everything seems perfectly okay. So now we move along to our response analysis, okay? We are making a subtle change here. Our inductor current, IL of T, because this is critically damped, should be of the form A1 T e to the minus alpha T plus A2 e to the minus alpha T. This would be the case if we didn't have a source still in the system. Because we do have a source still in the system, we are also going to add plus IL at infinity. Because we know that as T gets large, it's going to settle at this value, right? So at IL at 0, this becomes what? What happens to our entire first term? 0, because we're multiplying by 0. So we're just going to have A2 plus IL at infinity. And so we can do some mathematical manipulation here real quick. So IL at 0, negative 0.4 amps, is equal to A2 plus 0, because we knew that I at infinity is 0. And that is going to give us A2 is equal to negative 0.4. All right, so I've run into a little bit of an issue here. Let me explain what that issue is. Because our term at infinity is 0, this is actually just going to look like a natural response problem. So I'm going to call an audible, and I'm going to say that instead of looking at our inductor current, we're going to look at our capacitor voltage so that I have something that isn't 0 to show up here and mess things up a little bit. Okay, so I'm switching slightly. I apologize for not recognizing that was going to happen a minute ago. So we're going to have practically the exact same thing. Vc of T will be A1 T e to the minus alpha T plus A2 e to the minus alpha T plus Vc at infinity, which means we have at 0, Vc of 0 is A2 plus Vc at infinity, which gives us 8 volts is equal to A2 plus 2.5 volts. So A2 is equal to 8 minus 2.5 is 5.5 volts. All right. Everything seem okay there? All right, I don't remember what the derivative off the top of my head is, so I'm going to have to look at the thing real quick. So let's see. Our current I of T will be of the form C dVc by dt, which is going to be C multiplied by negative A1 T e to the minus alpha T plus, I think it's A1 minus alpha A2, yeah. All right. And I at 0 plus then reduces to what? Yeah, this whole first term goes away, so we're just going to have C times A1 minus alpha A2, because e to the minus alpha T is going to go to 1. So A1 minus alpha A2. I want to make out a very important point here, right? Our function, our original function, we have this plus y at infinity term. Our derivative should not have a plus y at infinity term, because when we take the derivative of this constant value, it's just plus 0, okay? So we only have the infinity term in our original function. It should not show up in our derivative-based relationship. Common mistake to be made, so I'm just trying to point it out, okay? So, based on what we have here, I at 0 plus, which is negative 0.4 amps, is equal to C, which was 1 millifarad, times A1, which we do not know, minus alpha, which was 200 units of per second, times A2, 5.5 volts. So with a little bit of algebra, we can figure out what A1 is. So negative 0.4, I divide everything by 0.001. Add 200. I'm going to use a numerical solver. I feel like I'm going to make a dumb mistake there. Negative 0.4 is equal to 0.001 multiplied by my unknown minus 200 times 5.5. Solve for x. A1 is equal to 700 volts. Okay. Seems excessively large. But, or actually, excuse me, A1 is equal to 700 volts per second, right? And it has to be volts per second because we know that this coefficient A1 is going to be multiplied by T, okay? So while that may seem like an unusually large number, it's actually fairly reasonable because it's representing a rate, not a specific voltage, okay? So for very, very low values of time, it's almost nothing. It's not, excuse me, it's not until time increases that we would see that A1 times T gets large, but then that thing is multiplied by a very small number because we have an exponential of a negative value, right? So we're having some large number being multiplied by a very small number. So even though that 700 seems unreasonable, it's all going to work out to actually fit in within the constraints. So our capacitor voltage, VC of T, will then be 700 T e to the minus 200 T plus 5.5. No, that's not right. 8. What's a... Oh, no, no, no. You're absolutely right. I'm having a brain fart. You're absolutely right. It should be 5.5. 5.5 e to the minus 200 T plus 2.5 volts. So A1 is in there, A2 is in there, and then the most common mistake I would see people make is forgetting to include the value at T is equal to infinity as well. So just to check ourselves, let's throw this guy into LT Spice real quick. Yes. So it's negative 0.4 amps because that is I at 0.
Okay.
Yep, I'm sorry. I apologize for that. Yeah. So this is I at 0 is equal to C multiplied by A1 minus alpha A2. Just putting in the numerical values.
Yes.
All right, so LT Spice. All right, so for our transient condition, we have a 5-volt source. $20 ohm resistor here. $20 ohm resistor here. This guy was 25 millihenries, I believe. And we have our capacitor here. I'm going to put my ground to be the bottom node. And let's see. I'm going to label that node as VC. So this is an important thing to pay attention to, especially when you're doing your homeworks. When I'm doing these initial conditions, I'm always going to set my ground to be at the negative polarity terminal of my capacitor, okay? Because if I don't do that, I have to create some weird mathematical expression to show what the voltage drop over my capacitor is. Whereas in this case, it's literally just going to be the voltage present at this node, VC. So set your ground to be at the negative polarity voltage of your capacitor. We're going to make, it's going to make your life easier. So for our initial conditions, we have the initial condition over our inductor was negative 0.4 amps. The initial condition over our capacitor voltage was 8 volts. And let's see, alpha is 200, so it's decaying at a rate of negative 200 whatever per second. Let's look at 50 milliseconds at first and then adjust from there if necessary. All of my components have values. Didn't put the capacitor value in, so I was mistaken. All right, I get it, I forgot. 1 millifarad. So here's our capacitor voltage. Yep, 50 milliseconds gives us plenty of time to see it settle. Let me add traces. And of course, it's right in the way of where I want to put stuff. So I have 700 times time times EXP of negative 200 times time plus 5.5 times EXP times negative 200 times time plus 2.5. Matches perfectly. So we did all of our analysis correctly. Thank you guys for catching me trying to turn that to 8 for no apparent reason whatsoever. Then me just having a simple brain fart. But again, notice here, So because I have this 700 times time, if I try to put in volts per second there, let's see what happens. I believe it's going to hate me. 700 volts per second, 5.5 volts, 2.5 volts. Doesn't know how to interpret. So it can't do a combination unit like that. So on your homework, again, just be very, very careful whenever you have a critically damped circuit that the scale on the right-hand side, which is the one corresponding to your mathematical function, is identical to the scale on the left-hand side, which is the one corresponding to your simulation signal, okay? If the scales don't match, you may have the exact correct answer, but it's not gonna show up that way. So pay attention to that. All right, that's enough out of me. Anybody have any questions on total response or series RLC circuits? Yes, sir. Right click anywhere in the plot area, click the add traces button. And then right here where it says expressions to add, you can do mathematical expressions on all of the different things, like all of the different signals, but you can also just type in mathematical expressions too. So I just typed in the thing, yeah. Just make sure that T in your analytical solution is replaced by the variable it keeps track of, time. And if you have a sinusoidal function, LT Splice only does things with angles expressed in degrees. So because we deal with angular frequency measured in radians per second, you're going to always have to multiply by a factor of 180 divided by pi to convert that angular frequency into a linear frequency. All right, that's enough jibber jabber out of me. I will see you guys not this Wednesday, but the next Wednesday after the Easter break. You guys have a good break. Work on homework or not, whatever, you're adults. So see you guys later.